Okay. Now I check the connection with Teams. Okay, there is the translation. Record, stop transcription. Okay, so we can start maybe. Okay, last time we have seen how to what are convolutional neural networks. So we have seen that we can use this type of networks to process and extract information from images. So we have a first part that is called the feature structure part, based on convolutional layer mainly. Then we have also pooling layers and a flattened layer usually, and that we can use to extract information features in automatic way from input images. And after this feature structure part, we have the flattened layer to pass from 3D information to 1D information. And then we have the classification part of the network called multi-layer perceptron that we have seen in the previous lesson that we can use to extract information and also to create the classification starting from the extracted feature. So in this case, for example, the input is a zebra, and you can see that in output we have the zebra with the 0.7% of probabilities, and then the output is, we can say, correct, since the output represent the class contained in the input image. And we have seen how it's possible to train convolutional neural network that are very similar to multi-layer perceptron, with the exception that the neurons in the convolutional neural network are displayed in a 3D fashion. And here you can see 3 different ways to train convolutional neural network. The first type of training is the training from scratch. The meaning is that we use the network training from 0. So we had only a random initialization of the weights. So the initial weights are set randomly. We don't have any information related to the weights. Therefore, to train this network, we have to use, we must use a large amount of training data, in particular annotated training data, since now we are in these lessons also we are in a supervised learning setting. And usually the training procedure, the training steps are long and very complex. And in this case, we have to use powerful GPUs in order to train our network, and the training procedure is quite long. As you can see in the image on the right, with this procedure, we train both the feature structure, represented here in green, and also the classifier, so the last part of the network. Second method to train and use our CNN, our convolutional neural network, is to use pre-trained neural network. So we use a network that has been already trained on a particular and a specific data set. And in this case, so you can see in the image on the right, that's in red color, we have both the feature structure and the classifier. So we use the network as is, the pre-trained network as is. So the output is defined by the previous training, and in particular, the previous data set that we have used during the training. And so if we have an excellent data set with very good annotation and the training is effective, we can have excellent performance. So for example, we want to predict the 3D head pose of a head in an image. We can download from the web, we can download from GitHub, for example, a network that is able to predict the head pose, and then we can use that network on our images. The third way is one of the most used way to train the network in our setting, we can say. and is the so-called fine-tuning procedure. We start from a pre-trained neural network. So we use, like in the second case, we use a pre-trained network. So a network that has been trained on a specific data set. Then we keep freeze the feature structure. We block the weights. We freeze the weights of the feature structure, so we don't change during the training procedure the weights of the feature structure. But we modify the weights only of the classifier, or the last part, the multi-layer perceptron of the network. In this case, for example, this procedure is used a lot since, for example, we want to start from a pre-trained network, but we want to modify, for example, the structure of the architecture of the classifier. For instance, we want to modify the final number of classes or something similar. Remember that the number of neurons in output correspond to the number of classes that we want to classify. So, for example, we download an architecture pre-trained on a dataset with, I don't know, 500 classes, but we want to classify only 10 classes. A solution can be represented by the fine-tuning procedure, in which we can download the network, we can freeze the feature structure, we can only update the weights of the multi-layer perceptron, so we can adapt the network to our problem. Usually, one of the most used data set to pre-train network in computer vision, and so in particular convolutional neural network, is the so-called ImageNet dataset, a dataset that contains more than 1 million of images of different 1,000 or more categories, classes, and is a very one of the most used dataset to train network and to apply this network after fine-tuning procedure to a variety of different vision-based tasks. So, for example, we want to classify, I don't know, if in an image there is a cat or a dog, we can download a network pre-trained on the ImageNet dataset, and then we can fine-tune our network in order to solve the problem about cat and dog classification. Okay, so with this slide, we have finished the part about convolutional neural network. Is the block number, I don't remember, 3.5, I think, 4 or 5. And then now we are able to start the last block, the last slide about the comparison between machine learning and deep learning. And this is a very important topic. So we can find several, not many slides, but a few slides, but these slides are very important since consideration about machine learning, deep learning are very important. This is a table that summarizes the comparison between machine learning and deep learning. And in particular, we focus on 6 main elements. The first element is data. With machine, in particular, training data, the data that we use during the training phase. For machine learning, we need large data, large amount of data. The meaning is of large is hundreds of data. So maybe if we have, for instance, a data set with 800 elements inside, training elements inside, it's better to use a machine learning approach since we have a large data set, but only with hundreds of different samples. For a deep learning approach, we need huge data sets, huge set of data, training data. Here, the meaning of huge is 1,000, but also 1,000, hundreds of thousand, million, thousand different training data. In particular, if we are in the category of training from scratch, we need a large data set to train the whole network, the whole weights of the feature structure and the classifier. If we are in the case of pre-train or fine-tune, not pre-train, there is not a learning phase. But In the case of fine-tuning, we need large amount of data, less data than the case of from scratch training. What is the accuracy? With machine learning, especially if training data have a good quality, we can achieve an high accuracy. And while with deep learning approach, we can have high accuracy, but we can say that we have the best accuracy in case of high dimensional data, and if we have huge training datasets. Okay, so if we have enough training data, we can say that deep learning usually provide best results in terms of accuracy. Training time, the machine learning our training time is limited, very limited. We can say that we are able usually to train a classifier or a regressor in using some machine learning library in a few minutes. Maybe we can have a training time of about 1 hour, 2 hours, many hours, depends on the quantity of data used. But we can say that usually we need we have to wait only minutes for the training time of machine learning approaches, and we need only the CPU, like as you can see in the following line of the table. So the required hardware for the machine learning solution is only the CPU, maybe a powerful CPU inside our computer, but that's all. We need only the CPU. With deep learning, we have a completely different approach, since we need a specialized hardware. In particular, we need a GPU, a graphic processing unit, especially with convolutional neural network. So maybe with MLP, we are able to use only the CPU, obtaining, we can say, standard training time. But with convolutional neural network and thousands of different images in input, we are forced to use a GPU. It's not scalable, this approach. So we need a GPU, at least one GPU. We can also have perform the training phase on multiple GPUs, okay? And as you can see, the training time is quite large. Maybe we need hours to train our model, but also days, weeks. And the last model released on the web, for example, for large language models or similar models, requires weeks of training on very powerful GPUs. So the training time and the required hardware is a critical element for the deep learning approach. What about features? We can say that with machine learning approaches, we don't have methods that are able to automatically extract features from data, in particular from high dimensional data or images. So we need to apply specific algorithms, such as, for example, the oriented histogram of oriented gradient or LBP features, in order to extract features from data. So the feature extraction is manual. We have to apply a method, then we have to define, to set all the parameters, and then we can extract the feature from data. While with deep learning, we have a feature extractor, that is the first part of the convolutional neural network, that is able to extract automatically features, visual features from images. So remember that in deep learning, the convolutional neural network is able to extract features thanks to the convolutional layer, while the last part of the network is the classifier that is not able to extract features, but only acts as classifier. Finally, there is a line about the interpretability of the methods. We can say that machine learning has a good level of interpretability. We can understand why, for example, we have a specific output of a machine learning algorithm, while with deep learning is much more complex. Usually, we are not able to understand why a convolutional neural network output a specific classification or a specific value if we have a regression problem, since it's too complex to see what happens inside the deep learning architecture, the deep learning network. This is a problematic element for deep learning. There are several research fields that are working on the interpretability of deep learning solutions, but we can say that nowadays interpretability for deep learning is problematic, is a problem. Here you can see a focus about the performance between and the comparison between machine learning and deep learning approaches. We have seen that with machine learning we can obtain high accuracy, deep learning best accuracy, specifically with especially with high dimensional data and a lot of training data and input. And here you can see this visual summarization. On the y-axis we have the accuracy. On the x-axis, we have the size of training data, the size of the training data set that we are using. You can see that if the size of training data is limited, usually best performance are obtained with machine learning approach. And then we have a point in which the performance of deep learning are superior with respect to the performance of machine learning methods, okay? The problem is that, as you can see here, is not easy to identify what is this point. It's not easy to say that, okay, with, I don't know, 15,000 of images, we have better performance with deep learning. It's not easy to say that. It's very complex. So we can only know that with a lot of training data, deep learning approaches are better than machine learning. So if you face or if you have to solve a problem and you have only a very limited data set, you can develop a solution based on machine learning. Or you can also think to use, for example, deep learning, fine-tuning the network. So you can download a network. You can download a pre-trained network on ImageNet, for example, and then you can fine-tune the network. Since we have seen that, I told you that the fine-tuning procedures requires a limited portion of training data. But if we have to train our network from scratch, we need a lot of training data. So if we don't have a huge training data set, deep learning is not a good option. Here you can see a slide that focuses on the hardware that we have to use for deep learning. As I mentioned, we need specialized hardware for deep learning. So before starting a project in your future company, for example, with deep learning, you need to ask if the company or the research laboratory has the necessary hardware. In particular, the required hardware is one or more GPUs available. Okay, without GPUs, remember that you cannot train a convolutional neural network. So GPUs are essential for parallelizing the computational load. Okay, and remember that if we add layers in our convolutional neural network, and also if we add neurons, we increment also the computational load of our network. So we need more powerful GPUs. Remember also that today the only usable GPUs for deep learning are produced by NVIDIA. So there is only a single company in the world that is able to produce the hardware that we can use for deep learning. We have a sort of competition introduced by Google thanks to the release of TPU, that are the tensor processor units on the market, but TPUs are not widespread and also a lot used. And remember that why we can use only NVIDIA GPUs, so GPUs produced by NVIDIA, since NVIDIA developed the so-called CUDA libraries, that are the libraries that we can use to use the GPUs. Okay, without CUDA library, we are not able to use GPUs for our deep learning algorithms. And that's why we are forced to use NVIDIA and GPUs. Maybe in the future, also AMD will develop a deep learning library that maybe will will be adopted by different research laboratories. So maybe in the future we will have also GPUs developed by created by AMD, but this is not the time. Remember that the training procedure may be quite long. So when you use deep learning solution, convolutional neural network, maybe you have to wait a lot for the training to finish the training procedure. And to buy the required hardware, we have two main solutions. The first solution is the in-house solution. So this solution consists in the fact that the company buys the necessary hardware, so is the direct owner of the hardware. And with this solution, we have some pros and some cons. For pros, we have an extreme freedom of the use of the hardware, and also in the long run, it tends to have lower costs since we buy the GPUs once and then we have our GPUs, and then we can use our GPU with a complete freedom. About the cons, we have to remember that hardware maintenance is required, so we need specialized technician in order to maintain the hardware, maintain the server in which there are the GPUs. We have to remember that, unfortunately, the hardware ages quickly. So, okay, we have buy some GPUs, but we have to invest over the time many times since we need to buy newer GPUs. And for a large number of GPUs, we need the specific room server with the control of the temperature, the access control, and so on. And also we have a very high energy consumption, okay? Remember that a single GPU, the latest generation of GPU, a single GPU is able to consume about 500 of watt of energy, so a large amount of energy. And finally, the GPU market is quite expensive and volatile since we have problem in the production of this chip. We can say that very few companies are involved in the production process of GPUs. One of the most important company, and also we can say one of the few companies that is able to produce the technology for GPUs is the TSMC, and we can have a shortage in the semiconductor production, and we faced this problem in last years. And also we have external elements, as usual, that can influence in a positive or in a negative way the markets, such as, for example, the rise of the mining or wars, unfortunately, and other external elements. The second solution for the hardware is external solution. So the hardware is rented through the cloud paradigm, in particular the platform as a service paradigm based on the cloud technology. So in this case, the hardware is not bought by the company. So in this case, the hardware maintenance is not required, and no investment over time are required for the hardware upgrades. And then we don't have dedicated server rooms in the company, since the GPUs are not located in the company, but they are in external company, in a third-part company, and the service is provided by the internet connection, okay, using the cloud technology. We have also some cons with this solution. In the long run, we can say that we tend to have higher costs since we need to rent the hardware, and then we have to pay to obtain the hardware. And then we have some cons related to the cloud-based solution. For example, the vendor lock-in it is difficult to change the service provider. If we start our research activity with Google, it's not so easy to transfer all the data, all the models, all the technology to, for example, Microsoft. So there is a sort of vendor lock-in. And also we can have problems with data, the privacy of data, since we don't know where are our data, since we have to upload usually our data to our cloud provider. So we don't know who really owns the data, and also so we have privacy issues. There are several services to have GPUs, for example, Google, and now in this course we use Colab, since we can use a GPU for free thanks to Colab. It's limited in time, but for our purposes, it is a good solution. And we have a service based on Amazon, for example. Maybe if I click here, the link is working or not. No, I can try to use. Oh. Okay, for example, this is the solution provided by Amazon, in which, for example, we can configure an Amazon machine, and you can see that, for example, we can choose the location type, the region of the virtual machine, the operating system of the machine that we want. It's based on Windows, Linux, and so on. And also we can, okay, here we can select the hardware that we want to use. And as you can see here, the hardware is related to the cost of the solution. So we can, for example, decide the number of virtual CPUs. We can define the instance family. As you can see here, there are a lot of possibilities, and you can see the documentation if you want to know something about this one. Remember that if you pay, you can obtain GPUs, of course, but you have to pay a good amount of money, we can say. Okay, so we have almost finished our course. We are going to do the last two exercises about the lab, and we are going to see a part about regression. But we can say that we have finished our course, our journey in artificial intelligence. Yeah. Yeah, there are some limits. So if you use the free version of Colab, you cannot ask a specific type of GPU. So you can have a free GPU, but you don't know the type. And the time is limited to 24 hours, if I remember well. If you pay, you can select the GPU, and maybe you have a longer time range. I'm not sure about, since I don't use Colab for the paid version. And yeah, you have higher limits, but I think that there are still some limits that you cannot, you have to observe. In-house solution. Yeah, it's one of the elements. Yeah. The problem is not the number of GPU usually, but is the cost. So when the cost explode, you have to buy an in-house solution or something similar, since for little projects, you can use also external solution. Other questions or not? Okay. So this is a sort of summarization of our course. We start from problem, and we have defined many problems. So for example, many tasks of AI. So for example, we have seen the classification task, the regression. We are going to see the regression task. And then we have the clustering task that you have seen during the data mining course. To solve this problem, a classification problem, a regression problem, we need data that of course are related to the problem that we want to solve. And to get data, we we, for example, have the data acquisition procedure, the data annotation that is very important, since remember that if we are in the supervised learning setting, we need to not only acquire data, but also annotate data. That is one of the most problematic part, expensive, time-consuming part of the data acquisition procedure. Or another solution is to download public datasets that you can find on the web. And this is the solution that we adopt in our course, since we have downloaded the Euclid dataset and also other dataset that we have used during our lab. Okay, we work in the supervised learning setting, and so our AI strategy can be is based on 3 different elements. So, for example, if we don't have training data, we have seen how it's possible to develop the so-called expert system that are based on the predefined rules. Okay, and we have seen many elements about this solution. Remember that usually they don't scale well, and they need a strong a priori knowledge, since we have to know how to solve a problem, and we can apply this knowledge only to solve a simple problem. Differently, if we have hundreds of annotated training data, so a limited portion of annotated training data, we can use a machine learning approach. In particular, we have seen some classifiers, the subtor vector machine, random forest, but also ensemble methods. And we have seen how it's possible to obtain an output using a classifier giving an input numeric data. If we have images, we can the input for input we can have an image flattened, so we can use a flatten technique in order to flatten the 2D dimension of the image and to have the input for our classifier. Or for high dimensional data such as images, we can use a feature extraction technique in order to have a vector of values that is the input of our classifier. All this part can be done with the scikit-learn package library. If we have thousands of annotated training data, usually we can have deep learning solutions based on neural networks. We have seen 2 types of neural networks, the multi-layer perceptron and the convolutional neural network, that are based in the last part on multi-layer perceptron. And we can apply the multi-layer perceptron with numeric data or image flattened. Remember that the input, the dimensionality of the input of the MLP is 1D, 1 dimension. So we have to flatten images, or we have to use numeric data inputs. With MLP, we can use also a feature extractor technique. Remember that MLP is not able to automatically extract visual features, since we don't have convolutional layer inside the multi-layer perceptron. And finally, with images, we can apply directly CNN, convolutional neural network. And in this case, we don't have the manual feature extraction phase, but the conv layer are able to extract features and then provide in output the classification or the regression value. Okay, so this is the summary of our course. If you have questions, please tell me. Let me see. Okay, we don't have questions. How many we are? 4. Okay. Okay, so now you can download exercise number 5, if I remember well, from Virtuale. Exercise about number 5, about classification with deep learning, and in particular with convolutional neural network. You have to download also the Euclid dataset and the Euclid dataset VL. That is a special version of the Euclid dataset with more training data. Okay, in the Euclid dataset, we have, if I remember well, 800 of training data, training samples, while the Euclid dataset, we have several thousand of training data. And then we can try to use this dataset for our exercitations. So I give you few minutes to do that.
Prof, mi sente?
See?
I have a problem with the file because I click on it, but it redirect me to like a notes, so not to
Okay. I have to specify. Let me change. You can click with the right button and then download the file, but I can also change to force the download. Okay, try now.
Okay, now it runs. Also, the last exercise, regression with machine learning.
Yeah, I upload now. Okay, I
Okay,
change
thank
now
you.
the input setting. You can also, meanwhile, upload the Euclid datasets, both versions. Okay, are you ready to start with the Colab?
Yes.
Okay, you in the room, are you ready? Okay. Okay, so we can start. Classification with deep learning using convolutional neural network. So as usual, we import TensorFlow and Keras libraries since, as I told you, we use TensorFlow and Keras to handle the complexity of deep learning solutions. Then we are going to use two different datasets, the deep learning version of the Euclid dataset for training and validation, and we can say the standard, the common Euclid dataset for testing. Since I repeat another time, with convolutional neural network, we need a lot of training data. So I created a special version of the Euclid dataset. So please upload the zip files of the Euclid datasets and then unzip each file on our virtual machine, running these two. And if we upload, you can see that we have two different folders. The structure inside the folders is the same. So we have 4 folders with the classes rectangle, rhombus, square, and triangle. Now we have the part about data loaders. How it's possible to load data for our neural network. Also in this case, like in the exercise about multi-layer perceptor, we use a method already available in the TensorFlow, in particular in Keras, that is the method image dataset from directory. And remember that in the first position, we have to specify the folder on which we want to load the data. So in this case, Euclid dataset DL is the deep learning version. The labels are inferred using the class names triangle, rectangle, square, and rhombus that corresponds to the 4 folders that we have in the dataset. Then we have the color mode or the images. In this case, I specify RGB. Maybe we can use also gray level images, black and white images. Then you can also try to modify these parameters. Here we have the batch size. Remember that is the size of the images that we process in parallel in the same iteration. Here I specify the image size 224 times 224. And also I have specified that I want to shuffle images of my folders. And then it's important to say that here the subset is the training and the validation split is 0.2. So if we run this cell, you can see that, okay, in the deep learning version of the dataset, we have 8,000 of samples belonging to 4 different classes. And for training, we use that 80%, so 6,400 images for training. Okay, they are not enough for training from scratch. Okay, so yeah, I upload an improved version of the dataset, but remember that is not enough, unfortunately. The validation dataset is the same, but we specify that we are in this validation subset, not in the training. So if you run the cell, you can see that we have 1,600 files for validation. The testing set is created using the same method, image dataset from directory, but sampling the images, the data from the Euclid dataset folder. So in this case, you can see that the validation split is 0. So we want to use all the images for our testing set. In the standard version of the Euclid dataset, we have 800 images, and then all 800 files belonging to 4 different classes are put in the testing set. Okay. Now it's time to define the model architecture, the architecture of our convolutional neural network. In this case, we have 2 options. The first option is to define our own architecture. So we can use the Keras methods in order to create a dense layer, a convolutional layer, a sample layer, a pooling layer, sorry. And then we can create our own network. The second option is one of the most used in the literature, usually for standard problems, is to download and use an architecture already proposed in the literature, an architecture that has been developed by a research laboratory in the world. In this case, for example, I decide to use the MobileNet CNN. Okay, so in this case, you can see that the model is defined as the MobileNet network that is contained in the Keras application class. If you search on Google MobileNet CNN, you can see that maybe I can. Maybe we can find the the original paper or other, for example, the Medium blog, in which you can see that there is the explanation of a well-known structure, architecture of the network, in which you can see that we have a lot of convolutional layer, we have an average pooling layer, we have a fully connected layer, we have the softmax activation function, since we want to solve a classification problem, and so on, okay? So for each network that you can find in Keras, you can see that you can find also the documentation, the technical documentation online. And you are able to understand the majority of the concept exposed here. We didn't have cover all the aspects, of course, since we have only 24 hours, but you can understand the main content of this technical documentation. For example, here you can understand that we have a convolutional layer. You can see also that we have a specific filter shape. Filter is the synonym of kernel, okay? This is the matrix, this is the filter that we put on the image using a sliding window process and using the convolutional operation. And in this case, we have 3 times 3 times 3, since we have a three-dimensional image. Or, for example, here we have a fully connected layer with this number of neuron, okay, 1D neuron, since we have 1 times 1 times 1024, okay? And, okay, this is the regression. So this is our network. What we can say here, what we have to specify? We have to specify, for example, the weights. This is very important. In this case, we are going to fine-tune our network. So we download the network, the weights of the MobileNet, train on the ImageNet dataset. So you can see here that I specify that I want the weights of our network, train on the ImageNet dataset. Fine-tuning, since we are going to change the last fully connected layer, since we want to solve our classification problem, in which we have only 4 classes and not 1,000 of classes of the ImageNet dataset. Okay. Another important element, for example, is here the number of classes. That is 1,000, since we are using the network pre-trained on the ImageNet dataset. And also we have the classifier activation, the softmax classifier, the softmax activation function, since we are in a classification task. So we want to use the softmax in order to use the cross entropy loss function. So here we can define our model. You can see that you have here a line that say downloading data from blah blah blah. These data are the weights that we are going to use, and the weights that belong to the MobileNet using pre-trained on the ImageNet data. Okay, so that's why you can see our downloading operation here. Now it's time to define our model. So we want to define to change the last fully connected layer. Remember that in this case we have 1,000 of classes, and then in the last fully connected layer we have 1,000 of different neurons. In our case, we want that the last fully connected layer contains only 4 neurons. That's why we have to change the shape of our model. So in the first passage, in the first step, we define a dense layer. Dense is the meaning of, is the synonym of fully connected layer, so dense layer, with 4 neurons. We have 4 classes, so I define 4 different neurons. Of course, we have the activation function defined as softmax. We are in classification task. And the name of this layer is prediction, since it's the last. Okay, the name is not so important, but in this case, we have that these layer contain the prediction of our network. This layer is connected to the last layer, the last convolutional layer of our network. Okay, in this way, I access to all the layer of our network. I remove the last layer, and then I connect the output of the last layer to our dense layer. Okay, so we have network here. Mobile network that in which we have an architecture. Okay, we don't know all the details, but we know that here we have the CNN architecture with conv layer, a pooling layer, and so on. Here we have a 1000 fully connected layer, also called dense layer. We have downloaded the weights for all the network. Now, what we are going to do, we have defined a final fully connected layer with only 4 neurons. 1, 2, 3, 4, with the activation and software activation function and so on. And then we are going to connect this layer, not with that, but with our network. Okay. And so the output now is, you can see in the second line, the model is composed now with the model input, so the input that we use in the old model, and the output of our dense layer. So in this way, we have created a new model that is based on the MobileNet architecture for the first part. And we have changed the last fully connected layer using 4 neurons, since we want to solve a problem with only 4 classes. That's okay. Therefore, we are going to apply a fine-tuning procedure. Okay. If you remember the slide. If you remember the slides, oh, where are the slides? Here. Is the third line. In this case, we want to freeze. We freeze, or we use the architecture of the first part of the MobileNet, and then we are going to change only the weights of the fully connected layer using a fine-tuning procedure. Okay. Okay. So we can run this cell. Yep.
Sorry, Professor, I have a question. If in the previous step, the step of our model, there is the key parameters classes, why don't we change that parameters instead of creating another value?
Since you are the number of classes, you will obtain an error, since the weights of the network trained on ImageNet contains 1000 of classes, and then if you download the same weights changing the number of classes, you will obtain an error, since you are trying to put 1000 of different weights in a fully connected layer, for example, with only 4 neurons. Okay. Have you understood?
Okay, so so the model, we cannot change the predefined MobileNet.
Yeah, if you want to download the pre-trained network, yeah, you cannot change.
Okay, so every time that we use this model, for example, we need to specify always that the output should contain the number of classes that we are analyzing.
Yeah.
Okay.
And then you have to create a new dense layer and you have to attach, you have to merge this dense layer with the old architecture.
Okay.
Okay. We can see also the structure, the architecture of our network using the summary method. And as you can see here, okay, we have a lot of conv layer, we have an average pooling layer, global average pooling layer, we have dropout that we don't have seen. And here you can see that finally we have the layer called predictions. Here you can see the name that we have specified above. That is a dense layer. And in this dense layer, we have only 4 neurons. Okay? And then you can see also the number of parameters, total number of parameters, trainable parameters, and non-trainable parameters. Okay, before starting the training procedure, we have to specify the elements that we have seen together also for the multi-layer perceptron. We have to specify the number of epochs, in this case 5, since the training is quite slow, so I limit the number of epochs, but maybe in your project you can increment this number. And we have defined 2 different callbacks. The first is the model checkpoint to save the weights of the model after every epoch. And also the callbacks related to logging, since we want to visualize the learning curves using TensorBoard. And finally, we are going to use the compile methods in order to compile our network. Note that here we are using the SGD, the stochastic gradient descent optimizer. Remember that if with fine tuning, usually it's best is the best option is to use the SGD optimizer with very small learning rate. From scratch, we can use usually Adam. Is better than SGD. But it's important that with fine tuning, we have to use SGD. As the loss function, we have the categorical cross entropy, and for metrics, we have the accuracy, of course. Then we can run this cell, and then we are able to run our training procedure. Remember to click on a runtime, and you have to change a runtime type, and then you have to ask for a GPU. And in my case, I already have the GPU. If you click here on the right, you can see that I have the RAM memory for the system, but also the RAM memory for our in our GPU. So I know that I have already requested the GPU for my virtual machine. There is also here the name of the GPU, T4. And if you don't have the GPU, here you have only 2 plots, the RAM of the system RAM, and the disks. So remember to to ask for a GPU, and then we can click. And as you can see here, maybe the training procedures is quite slow. Even if we don't have a lot of training data, and even if the architecture that we are using is the MobileNet architecture that is a quite light architecture, we can say. Okay, it's not a very deep architecture with an high computational load. It's an architecture developed for embedded system with limited hardware resources. So I chose an architecture that is quite fast in training. So we can say that we have the first epoch, and then we have to wait for all the 5 different networks. Epochs that I specify above.
Prof, in the meantime that the models run, do you have some news about the fact to do the exam of machine learning and data mining separately, or we need to do them within 1 month?
No, they are separate. So there is not the requirements of 15 days between the two exams.
Okay, thank you.
And sorry, I have another question about the exam. Usually, how long does it last? So, for example, let's say that I take the project of data mining, and so I will come to machine learning only to do the oral exam. How long would that last?
I don't know. Maybe 1 hour, maybe 30 minutes. Depends on the answer and depends on the level of preparation.
Okay, so more or less like between half an hour or an hour each.
Yeah, we can say that.
And can I ask something else? Usually, how many questions are you going to ask during the exam?
There is not a fixed number of questions. Depends on your ability, your knowledge, your preparation, and so on.
Okay.
Okay. Okay, we have almost finished our training procedure. Only 5 epochs. Usually you have to usually you have to wait for 50 epochs, 100 epochs, so you can understand the time that we have to wait in order to have our network trained. So the fitting procedure is finished. We can analyze the outputs of our procedure. So you can see that, okay, here we have a warning, but it's not important for us, since we have a usage warning about, okay, we are saving our model using this HDF5, but it's not important, okay, for us. You can see that the loss value at the beginning is quite high. We have 0.26. And then we are able to reduce the loss error across several epochs, across 4 different epochs to 0.06, 3, 2, and 1. Probably with other epochs, we are able to further reduce the loss error. And you can see also the accuracy. The accuracy is quite good, since we have an accuracy of 0.9, 98, 99. But remember that is the accuracy on the training set. So it's quite easy to have a high accuracy on the training set. While with in the validation set, we have an accuracy of 0.94. Okay, it's not a so complex data set. And you can see that we are able to increase the level of accuracy across several epochs, but in this case, the last epoch is not the epoch with the best accuracy. So remember to use the weights that correspond to the best accuracy that you have obtained during the validation procedure. Okay, we have trained our network. You can see that here we have also the weights of our network. And here you can see the number of epochs, 1, 2, 3, 4, 5. And here we can evaluate our methods, our model. And the first things to evaluate our model is to load the model, to load the weights of our training model. So here we can decide to load the weights, for example, after the first epoch, after the second, the third, and so on. In this case, we can see that the best epoch is the epoch number 4 here, since we have a validation accuracy of 95 and the lowest validation loss. So I can here specify the number 4. And then I can evaluate our method. To evaluate our method, our model, we can use a Keras method and evaluate method in which we have to pass the testing dataset. We don't have labels here, and you have to decide the batch size and not other important elements. So you have to specify the most important element here is the testing set on which you want to test your model. We can run this cell and we can see that we have 25 iterations since we have a batch size of 32. So if you multiply 32 with 25, you obtain the whole training size. And you can see that the accuracy is quite good since we obtain a low loss value, but in particular, a very high accuracy, 0.96% of accuracy. That is a very good value, okay? So thanks to the use of convolutional neural network, we are able to solve a classification problem in a very fast way, okay? So maybe here you can appreciate the powerful of our neural network, okay? We don't have a lot of training data, it's true, but also we can say that the classification problem is quite simple, it's quite easy. So we have obtained a good final results. For example, if I use the weights after the first epoch, we can expect lower results. Let's see. After the first epoch, we have an accuracy of 0.82. And then you can understand that it's very important to use the weights of the right epoch. So during your training procedure, you have to identify the right epoch, and then you have to use the weight produced after this specific training epoch. You can help yourself using also the TensorBoard module. That is pretty important since you can understand the learning curve, and so you can see if there are overfitting phenomena or something similar. In this case, you can see that, okay, it's not working. Okay. Okay. Is better. Okay. In orange, you can see the train. In blue, the validation. Of course, the training, the accuracy of the train is higher than the validation. And you can see that across all epochs, we are able to increment the level of accuracy of our network. Okay, here you have the smoothing. So remember to also put the smoothing to 0. And now you can appreciate that after the third is the fourth epoch, we have the best accuracy in the validation set. Okay, using smoothing of 0.6 is not possible to appreciate this thing. So maybe you can you use the weight produced after the fifth epoch, but in reality, the best weights are after the fourth epoch. Okay, so it's important to play with the smoothing factor. Here you can see also the epoch loss. And of course, the training curve is lower than the validation curve. And also in this case, it's important to see that after the fourth epoch, we have the minimum loss value that is not after in the last epoch. So it's important also to check this plot of the learning curve. Okay, and this is the evaluation. Okay, accuracy. Do you have a question about this part? Okay. If there are not questions, we can have a 5 minutes break, and then we can continue with the regression part. Remember to download the exercise number 6 from Virtuale, that is regression with machine learning. And also there are new, the slide number 5 with regression. See you in 5 minutes. Yes.
Allora, un dubbio sull'esame. Se una persona fa l'esame, viene col gruppo, spiega il progetto, fa la parte di machine learning, poi fa la parte di che lo stesso giorno, giusto?
No.
Anche in giorni diversi, ok? Se poi non è soddisfatto del voto generale, vuole ridarlo per prendere un voto più alto, deve rifare anche la presentazione del progetto che ha già fatto col team la prima volta? Perché, per esempio, se siamo in 3, 2 accettano il voto, uno no perché vuole prendere un voto più alto. Quella persona che vuole prendere un voto più alto, la volta che ridarà l'esame, deve rispiegare anche il progetto che ha fatto con le altre 2 persone?
No.
Solo tu?
Sì, per la mia parte è così. Per la parte del prof Golfrelli direi che siamo avanti al 5% così. Chiedetelo per conferma, ma direi di...
Però quello solamente nel caso si faccia il progetto con Golfarelli, chiaramente. Cioè, ovviamente se lo facciamo noi.
Con me, sì.
Quindi io so che- Quindi, è così. No, poi lo prendo in mano. Ah, sì, ciao. Sì. Gli facciamo vedere come si fa. Allora, guarda.
Okay. Okay. What about regression, the last topic of the course? We have seen the details about regression in different slides of our course. So you can find, for example, the definition of the task regression in the slide number 6 of PAC 3.1. So if you go in the PAC 3.1, slide number 6, we have seen that the regression task is a task in which we have a regressor that outputs a continuous value. So in input, we have some data, numeric data, we have an image, we have something similar. In output, we have a value, a continuous value. And this is different with the classification task, in which in output, we have a classification, okay? Only for example, just only to better highlight the nature of the regression task, we can see the regression task has a classification task in which we have a very high number of classes, or we can say that each continuous value corresponds to a different classes. The other aspect important is that regression models are different from classification models. You cannot use classification models to solve regression tasks. In the scikit-learn package, you can find, you have the SVM, the subtor vector machine, developed for the classification task, but also for the regression task. So for the classification is SVC, support vector classifier. For regression is SVR, support vector regressor. The same with the ensemble methods and random forest, for example, or decision trees. What else? Okay, regression in machine learning. As I told you, you can find the theory is equal, since we have the classifier that we can use also for the regression task in the regression type. Okay, they are adapted also for the regression task. Remember that they are different. So I repeat, for example, for the SVM, we have SVC, that is the classifier, and SVR, that is the regressor. And this is the same happens also with ensemble methods. So there is nothing new to introduce for the regression in machine learning. With deep learning, also in this case, the theory is almost the same with respect to the classification task. but we have a difference. We have some differences in the loss function, as usual, since we have introduced loss function for the classification task. In particular, we have introduced the cross entropy family, in which we have the binary cross entropy, the BCE loss function, that is the function that we can use, the loss function that we can use for binary classification problems. And then we have the multi-categorical cross entropy function, that is the loss function that we can use for problems, classification problems, in which we have more than 2 classes. For the regression task, of course, we have to introduce specific cost function, loss function. Here you can see 3 different loss functions that you can use for your regression task. The first is the root mean square error, RMSE, one of the most used loss function for regression, and is the average of the square of the deviation between the true value and the predicted value. So remember that also in this case, to create the cost function, we need the annotation, that is the ground truth, and the prediction of the network, that is the prediction value, the predicted value, sorry. The predicted value is P, the letter P. The ground truth value is GT. So in this case, we apply the square, the root square root over the differences between the predicted value and the ground truth value using the power of 2. In this case, we don't have negative values since we have the power of 2 here. We average all the values using 1 over n, where n is the number of elements on which we compute the root mean square error. And finally, we apply the square root. This is the root mean square error. If you remember the name, you remember also the equation since is the same. We have also other 2 variations of the root mean square error. The first is the so-called mean square error, MSE. So also in this case, it's quite easy to remember this equation since we don't have a root mean square error, but only mean square error. And as you can see here is the difference of the predicted values and the ground truth values. Then we use the power of 2, and then we average this value on all the elements on which we compute the mean square error. The last variant of RMSE is the mean average error, MAE, in which instead of the power of 2, we have the absolute value here. So we have the absolute value, the difference between, of course, the ground truth value and the predicted value, average on all the samples in the dataset, or that we are taking into account to compute our loss function. Remember that in all these functions, there is the letter E. That means error. So we have error here, and error here. And then low values of root mean square error, and mean average error indicate good performance of the regression model. These are errors, so low values indicate good performance. Then we have to introduce some metrics for the regression task. Then we can open the metric, and in particular slide number 8 to 10. Okay. The interesting thing, and also the good, the positive element for you is that, of course, we can say we can use the loss function also to compute the system performance, since we can use the same equation to understand if the predictions are good or not. We can compute the error between the ground truth and the predicted values in order to understand the system performance. So we can use the same metrics to build the loss function, or also called cost function, but also we can use these metrics. This equation has metrics to compute the system performance. So I don't repeat the details about this slide. And we have also another metric that is the coefficient of determination, R squared. That is the proportion of the variation in the dependent variable that is predictable from the independent variables. Okay. R is maybe a quite complex sentence, but you can understand that the R squared provides a measure of how well observed outcomes are replicated by the model. Okay. And why we introduce this metric? Since usually it can be more informative than the other error-based metrics, as since the result, the final number of this metrics is expressed as a percentage. So it's more easy to understand what is the output, the meaning of the output of this metric. Here you can see the equation. The formula of this metric is 1 minus SS, the residual sum of square, over the total sum of the square. And what is the meaning of this one is the sum of the, we have seen before, the difference using the power of 2 between ground truth and predicted values. And as thought is the sum of the difference between the ground truth values and the average of the ground truth values. Remember that this is a percentage. So in the best case, when we have a very good regressor, R square is equal to 1, while in the worst case, we have R equal to 0, or even with lower values than 0. So the models, in this case, we have a models that have a worse prediction than the average value. We have a negative output. Let's see an example of these regressions metric. Is a table very similar to the classification table. Okay, so that we have seen before, in which we have a classification between dog and cat. So we have a table that represents here the predicted values. Remember, we are in the regression task, so we have continuous values in outputs. And then we have also the ground truth values. So in this case, the ground truth value is 12, and the predicted value is 14. In this case, it's 25, while the ground truth value is 20. So we have an error between the prediction and the ground truth. Here you can see all the calculus that we need to measure the mean square error. In this case, the mean square errors, if you do all the calculus, is 16. And you can understand that it's not so easy to understand what is the meaning of 16. We know only that low values indicate good performance, but we don't know exactly what is the meaning of 16. This is the problem with mean square error. We cannot compute also the root mean square error, so we can apply the root square on 16, then we obtain 4. We can also apply the equation to compute the mean average error is 3.2. And finally, we can compute the R square, in which that outputs a value of 0.14. Okay. 0.14 means that we have a quite good model with not so high error, since we know that 0.14 can be intended as percentage, that is the deviation of the model with respect to the ground truth values. Okay. In general, we can say that I repeat, is not so easy to understand using a single value if the model is good or not, the performance are good or not. Maybe we can compute the root mean square error across several epochs during our training procedure, and then we can understand if we are able to reduce the error or not. Okay. Okay, and here we have all the other metrics. So we can say that where is regression? Okay. Now you have all the knowledge about the regression. So the theoretical part is almost the same with the classification part. Remember that you have specific elements that are different from the classification task, in particular the loss function that you use in deep learning, and also the metrics that are similar, are the same of the loss function, but we have also the R-square metric. Okay. If you open column number 6, where I put the citation, we can see the regression with machine learning. Okay, so we can activate the virtual machine. In this case, if I remember well, you have to upload the shapes.txt file, not all the zip folder, but only the shape.txt file. So Euclid dataset here and the shape.txt file. Okay. Okay, so in this case, we are going to use the same dataset of the previous exercitations, so the Euclid dataset. And in this case, the regression task is that we want to predict the position of the centroid, the barycenter, of our geometric shapes in our dataset. So in this case, you can understand that the output is not a class, is not the class rectangle, rhombus, square, and triangle, but the output is represented by two continuous values that are the two coordinates, x and y coordinates of the barycenter of our geometric, of the input geometric shape. Okay, so in this case, we have a regression task with two values in output. As a first step, we can import the Schicklr library. Of course, since we are in the realm of machine learning. We have the class point. I'm not sure that we are going to use this class, so it's not so important. Okay, here we have a method, getLabels, that has the name of the method set. It creates the ground truth annotation. So you can see that if we have 6 different coordinates, the centroid is computed using the x and y values divided by 3, is the formula of the barycenter, okay, the centroid of the triangle. While if we have 8 coordinates, so we have, this is the other case, we don't have only 6 coordinates, but 8 different coordinates. The centroid in x and epsilon is computed using the same approach, divide by 4. Finally, we return the coordinates, x and y coordinates of the centroid. So we can run this method. And here we have the method to prepare data, that is the same function that we use in our exercitation in machine learning. And you can see that the structure is the same. So we are going to exclude the triangles for simplicity, but you can try to also include triangle in your computation. And then we are going to create 2 lists. The first list that we return contain coordinates of the geometric shapes, while the second list contain the labels. Remember that in this case, the labels, a single label contains the 2 coordinates of the centroid of the geometric shape. Okay, here we have the body of the solution. So the first step is to, of course, open the shape.txt file and read all the content, all the line of the shapes.txt file. And in the standard version of the Euclid dataset, we have 800 lines. Then we have to shuffle the dataset since we have to mix all the geometric shapes. And as you can see here, at the beginning, we have triangle, but after the shuffling procedure, we have different geometric shapes. Then we have to create the training, validation, and testing sets. In particular, we put the 20% of data in training, 20% in validation, and the 60% in the test set, using the method that I showed you last time. The other in the that I showed you in the other exercitation about machines. Okay, remember that you can use also the method provided by the scikit-learn package that is called train test split. But in this case, you need to have other data structure that are different from this exercitation. So you have to know that there is also this method. You can use this method. You can read the official documentation about this method. And it's possible to use this method in your final project. So you can use it, or you can use our way to divide and create training, validation, testing sets. Now it's time to prepare data. Remember that prepare data function method return a list of X training or coordinates and labels. And as you can see here, we have 361 samples in the training set, about 100 in the validation, and in the set for a total of 600, since we have excluded the triangles from our computation. Now there is the real difference between with respect to the classification code. Here, remember that you have to import the regressor, not the classifier of the scikit-learn package. And in this case, we are going to use, as you can see here, the support vector machine implemented as a regressor. So in this case, remember the name is SVR, support vector regressor, is not the SVC, support vector classifier. With this regressor, we can output, we can predict in output only one value. So if we want to output more than one value, we need the multi-output regressor system available, method available in the scikit-learn package. Okay, remember that in output we have two different values, since we have the X and Y coordinates. That's why we need the multi-output regressor. If you have only one value in output, you can use only the SVR method, for example. Or, as you can see here, we have the MLP regressor, okay? That is the multi-layer perceptron implemented as regressor, okay? Then we can run this cell. And now we are ready to train our regressor. So we can run the fit method. That is quite fast since we are in the machine learning realm. So it's quite fast. So we have fit our, oh, sorry, here I forgot to change CLF. Okay, maybe you can put RGR. The meaning is the regressor, okay? Or RGS is not important. Here I forgot to change CLF, that is classifier, but is the same, okay, from an implementation point of view. So here I'm training the regressor, and now I'm ready to validate our regressor using the score method available in the scikit-learn package. As you can see, we have a great validation accuracy of 0.86. That is quite good. Remember that in this case, we don't have an accuracy, but we have a metric that is based on the fact that we are using the regression metric. You can check the official documentation to check the accuracy of the validation. And here we have also a part in which we can draw the predicted values that can be interesting, I think. And in particular, we are going to predict only the okay. We have all the prediction, and then we are going to predict only the first 5 predictions, so to print only the 5 prediction. As you can see here, we have a list of lists, since we have the list of the output, and in this list we have several lists that contain the x and y coordinates of our centroid. Okay. We can also here we can see also here a visual comparison between the predicted samples and the ground truth samples. In this case, the ground truth for the first case is 9770. Unfortunately, we obtain 101 and 74 that are quite different from the ground truth. So the error here is significant. Lastly, we can print, and also we can visualize the prediction of our method, of our regressor. And as you can see here, we are going to see only the first 4 prediction for simplicity, but you can change these values. And we are going to draw our prediction on a white paper, we can say, that is obtained using the np.once method that create a white matrix, a black matrix using this shape, 800 times 800 times 3. Since I want to use the RGB colors to highlight the different points that I want to predict. I multiply the ones with the 255 in order to have a white image at the final. For each prediction, I'm going to draw a circle. Okay, so we have only 8 coordinates, not 6 coordinates, so only case with 8 coordinates. So for each figure, we can draw the position of the vertices, and then the position of the prediction using a circle RGB, so a blue circle, and also the ground truth prediction using a green circle. Okay. We can see. Okay, here we have. Okay, for example, in the first case, we have a rhombus, and you can see that in green, we have the ground truth value, the ground truth position of the centroid of the barycenter, and our prediction is in red. So, okay, we have missed some pixel, so we have an error based, we have an error since we have seen that the predicted values are not equal to the ground truth values, but from a visual point of view, we obtain a quite good prediction, since the position of the predicted centroid is very similar to the position of the ground truth centroid. Here we have another rhombus. Here we have a square, I think, and you can see that with square, our prediction is much more close to the ground truth values. So it's a good element. We can use the term -1 here to indicate that we want to use fill in. Okay, you can note the difference now. We want to use circles that are filled with color. Is better for visualization. You can obtain this using the input parameters -1 in the circle method. Okay, here you can see that, of course, in scikit-learn, we have the metrics that I showed you before. For example, we have the mean absolute error, we have the mean square error, we have also other regression-based metrics. And so we can use this method. In input, we give the ground truth values, the predicted values, and we can see that we are able to compute the the two, the average value and the standard deviation of each metric that we want to use. And that's all. Okay, so the regression task is quite easy, is quite similar to the classification task. Remember that you have to use specific metrics, error-based metrics, and then you have to use specific regressor that are contained in the scikit-learn package. You can see here a list of exercise or homework that you can do to improve your ability with the code. You can, for example, implement your own mean average error or mean square error if you want. You can try also different regressors. So we have seen the SVR, the support vector regressor, but you can use also the multi-layer perceptron, the multi-layer regressor. You can use random forest. You can use AdaBoost, what you want. You can also try to install other packages, such as, for example, the package XGBoost, that is a package for boosting, as the name reveals. You can also try to include the in-input data triangle. You can try to normalize data in a better way. We didn't have normalized data in these examples, but you can try to do that. And also you can try also different data splits. So you can vary the amount of samples in the training set, in the validation set, in the testing set to see how this influences the performance of the final method. Okay. Okay, so we have finished. If you have question about the regression, you can ask me. Otherwise, I can give you some minutes, or also, we have maybe also 2 hours in order to have to complete this exercitation or something similar. In any case, we see you, have a good holidays, and see you in the day of the exam, of course.